Today, we are diving deep into one of the most fundamental ideas in all of math and engineering, Fourier analysis. It's kind of the hidden language behind everything from sound waves and Wi-Fi to how we process images. So let's peel back the layers and see what's inside. So let's just start with this visual puzzle. Take a look at this. This incredibly intricate shape is being drawn by, well, a whole swarm of simple little arrows, each one just spinning in a perfect circle. So the big question is, how on earth can all that simple, predictable clockwork motion add up to something so complex and specific? That's what we're here to figure out.
I mean, just look at it. Each individual arrow is doing the simplest thing imaginable, just rotating. But together, somehow, their combined effort creates this incredible coordinated dance. It feels like chaos, but it's the exact opposite. And the most amazing part? This isn't some random natural phenomenon. We can control this swarm completely with mathematics to draw literally anything we want.
All right, so here's our game plan to unravel this mystery. We're going to start with the idea of drawing with circles. Then we'll trace the whole idea back to its surprising origins in, well, heat. After that, we'll build our own intuitive frequency machine, explore the incredible superpowers this gives engineers, touch on a deep truth about signals and uncertainty, and finally get to the deepest why of it all with something called the eigenfunction perspective.
Okay, first up, drawing with circles. Let's get right into it and dissect the math behind that amazing animation we just saw.
So what you were seeing is something called a complex Fourier series. The core idea is that basically any path in 2D space can be built by adding up a bunch of simple rotating vectors. Think of it like a recipe. Each vector has a size, a starting angle, and a constant spinning speed. By choosing just the right combination, the right recipe, the tip of that final vector can trace out almost any shape you can imagine.
All right, so now that we've seen this really cool modern visualization, let's rewind a lot. Turns out this whole idea has its roots in a 200-year-old physics problem that had nothing to do with drawing. Yeah, the story of Fourier analysis doesn't start with pretty pictures, it starts with heat. There was this guy, Joseph Fourier, and he was completely obsessed with understanding how temperature flows and distributes itself, like along a simple metal rod. He even developed a famous heat equation to describe it. Now, the idea Fourier came up with, well, it was totally radical for its time. The top mathematician of the day, a guy named Lagrange, had already argued that there was no way you could represent a shape with sharp corners using only smooth, wavy things like sine waves. So when Fourier came along in 1807 and claimed he could do exactly that, his paper was flat out rejected. It actually took over 20 years before his ideas were finally formally proven and accepted by the establishment.
Now, to be fair, the idea of using waves as building blocks wasn't completely out of left field. Physicists had already figured out that something like a vibrating guitar string could be described as a sum of simple sine waves. But what Fourier was proposing was on a whole other level. He said, forget just naturally wavy things, I'm telling you we can build any function, even ones with sharp edges, out of these smooth waves.
To really feel how nuts this sounded at the time, think about it like this. Can you build a sharp, vertical cliff face just by piling up a bunch of smooth, rolling hills? I mean, intuitively, the answer feels like a hard no. It just seems impossible. Let's go back to his heat problem. Imagine you have two metal rods, one really hot and one cold, and you stick them together. The temperature graph is what we call a square wave. It's flat, then has a sudden, sharp jump. A sine wave is the polar opposite. It's perfectly smooth, constantly curving, with absolutely no corners. And Fourier's claim was that he could build that jagged square wave just by adding up a bunch of these perfectly smooth sine waves.
So what was his secret? His big insight? You can build a cliff from hills. You just need an infinite number of them. See, any finite sum of sine waves will always be perfectly smooth. It'll just be an approximation. But the moment you take the leap to an infinite sum, the rules of the game change, and that limit can become something totally different, something that actually has sharp corners.
And there's this fascinating little quirk that comes with this, called the Gibbs phenomenon. It turns out that right at that sharp jump, the approximation will always overshoot the real value by about 9%. And the weirdest part? That 9% overshoot never goes away, no matter how many thousands or millions of waves you add to your sum. It was so bizarre, the guy who first measured it accurately thought his scientific equipment was broken.
Okay, so this is all great, but it brings up a huge question. How do we find the right recipe of sine waves for any given signal? To do that, we need some kind of machine that can take a signal and unmix all the frequencies inside. So welcome to the frequency machine.
So our starting point is what we call the time domain. This is just the signal as you'd normally see it unfolding over time. Think of it like a smoothie, where all the different ingredients, all the different frequencies, have already been blended together into one jumbled up line. Our goal is to unmix it and find the original recipe.
And the intuition for how we do this is just brilliant. Imagine we build a winding machine. The process is simple. You take your signal, you literally wrap its graph around a circle, and you pick a speed for how fast you wrap it. Then you just find the center of mass of that new wrapped up shape.
Okay, but why on earth would we do that? Well, for most winding speeds, the signal just kind of smears itself out evenly around the circle, and so its center of mass stays right near the middle, at the origin. But, and this is the whole key, when your winding speed perfectly matches a frequency that's actually in the original signal, bam! All the peaks of the wave line up on one side and all the troughs line up on the other. And that imbalance yanks the center of mass way off to one side. That's the signal we're looking for.
So what we do is we just test every possible winding frequency one by one. And for each one, we plot how far the center of mass moved. The new graph we create is called the frequency domain. Instead of showing signal strength over time, it shows signal strength over frequency. A big spike on this graph tells us that its corresponding frequency is a major ingredient in our original signal.
Okay, so this winding machine is a great mental picture. But what's the actual math doing all the heavy lifting? Well, it all comes down to one of the most beautiful and powerful formulas in all of mathematics, the complex exponential, e to the I times t. This elegant little formula is the perfect mathematical description of a point moving in a circle. It is the engine of our winding machine.
And using that engine, we can write down the formal equation for finding our frequency ingredients. Now I know, this can look pretty scary when you first see it, but I promise, if you just keep that winding machine analogy in your head, it's actually incredibly intuitive.
All right, let's just walk through it. That f of t is just our original signal, the drawing, the sound wave, whatever. Then we multiply it by that e to the minus j omega term. That's our unwinder. It spins everything backward at the exact frequency n that we're looking for. The result is that the one vector spinning at frequency n is made to stand perfectly still, while all the others are still whizzing around. And finally, that integral sign just means average the whole thing. And what happens when you average a bunch of spinning vectors? They all cancel each other out to zero. The only thing that survives the averaging is our one stationary vector. And boom, that's it. That's our coefficient.
So, we've got the what and we've got the how. We know we can break signals down into their core frequencies. But so what? Why does this matter? Well, let's talk about the engineering superpowers this unlocks.
And let's start with the big one, superpower number one, the convolution theorem. And this is no exaggeration. This is basically the holy grail of signal processing.
See, in the normal time domain, if you want to figure out how something like a filter will affect your signal, you have to use a mathematical operation called convolution. And trust me, convolution is a beast. It's messy, it's complicated, it's just hard. But here's where the magic happens. If you use the Fourier Transform to jump over into the frequency domain, that horrible convolution operation becomes simple multiplication. I mean, just think about that for a second. It turns gnarly, difficult calculus into basic grade school arithmetic. It is an absolute game changer. And engineers who work with this all the time develop this amazing intuition. They can just look at a signal and know what its frequency fingerprint looks like. They know that a sharp pulse in time is going to be a wide range of frequencies. They know a pure sine wave is just going to be two perfect little spikes. It's like having a visual dictionary to translate between these two powerful languages. And that's just scratching the surface. There's modulation. That's literally how radio, Wi-Fi, and 5G all work. You're just shifting a signal's frequencies up or down. There's filtering. Your noise-canceling headphones are using Fourier Analysis in real time to find the frequencies of the background noise and subtract them out. And maybe most important of all, there's sampling. The very foundation of all digital technology, from music to photos, is based on knowing exactly how fast to sample a signal to capture it perfectly. That all comes from Fourier.
Okay, now let's step back from the hard engineering for a moment, because it turns out there's a much deeper, almost philosophical truth baked into all of this.
You've probably heard of Heisenberg's uncertainty principle from quantum physics, right? This idea that there's a fundamental trade-off, that you can't know both a particle's exact position and its exact momentum at the same time. Well, guess what? That isn't some weird magical quantum thing. It is a direct mathematical property of the Fourier transform itself.
And you can see this trade-off with any signal. Think of a sharp clap. It's very precise in time, it happens in an instant, but its frequency content is a total mess, a noisy smear of all kinds of frequencies. Now, think about a pure note from a tuning fork.
It's incredibly precise in frequency, right? It's just one perfect spike. But is it precise in time? Not at all. It has to ring out for a while to even exist. The bottom line is, you can have a signal that's short in time or one that's narrow in frequency, but you can never ever have both at once.
All right, this brings us to our final, and maybe the deepest point. We've seen what Fourier analysis is and how it's used. But the biggest question is why? Why does this work so perfectly? Why are sine waves the correct building blocks for analyzing so many systems in our universe?
The answer has a very fancy name, an eigenfunction. But the idea behind it is actually pretty simple. An eigenfunction is a special, magic kind of input you can feed into a system, where the output you get back has the exact same shape as the input you put in, just scaled up or down a bit. Its fundamental character is preserved perfectly.
And here's the punchline, the grand finale. For a massive class of systems that we see all over the real world, engineers call them LTI systems, but just think of circuits, speakers, mechanical filters, you name it. Their magic inputs, their eigenfunctions, are complex exponentials. They're sine waves. That means if you put a pure sine wave into one of these systems, what you get out is the exact same pure sine wave, just maybe a little louder or a little quieter.
So, do you see now why this is so unbelievably powerful? Fourier analysis acts as a universal translator. It takes any complex, messy input signal you can imagine and breaks it down into the system's own native language, its eigenfunctions. And since we know the system's response to each of those simple pieces is also very simple, we can figure out the total output just by adding up all those simple responses. It turns a hopelessly complex problem into an elegant three-step process. Break it down, analyze the simple pieces, and build it back up.
Ultimately, Fourier's great insight wasn't just about math or engineering. It was an entirely new lens for looking at the world. He showed us that so much of the complex, chaotic reality that we see around us can actually be understood as a simple sum of elegant, predictable parts. It's a powerful reminder that sometimes the most bewilderingly complex things are really just simple ideas added together.